Good afternoon, everybody. I hope you're having a wonderful day. We're going to continue our discussion here on gases in Chapter 5. And we talked already about Boyle's law, Charles' law, and Avogadro's law. And if we take a look at each one of those, we are talking about pressure, volume, the number of moles, and temperature. And if you take a look at the ideal gas law, we have all of those variables in there. So can I use that instead of the others? Of course. You just have to be aware of what is being held constant. Is it pressure? Is it volume? Is it the temperature? And then you can go ahead and use the ideal gas law. Sometimes you might have to calculate it more than once depending upon what is being held constant. Now, the ideal gas law is an experimental equation, and we have our universal gas law constant, which is our value R here, and that's basically a fudge factor, meaning that it is a factor that if we plug this in, 0.08206, pay attention to the units, liters, atmospheres, mole, and Kelvin. This tells you what the pressure, the volume, and the temperature must be in. We must be in liters. We must have pressure in atmospheres. We have to have our temperature in Kelvin. But what this does is it levels the playing field with all the different types of gases. So this is a really important point that I have right here. Gases behave ideally at low pressures and high temperatures. I guarantee that you will see that more than once. So here's some diagrams to help you support that. Ideal gases behave ideally at low pressures and high temperatures. So if I look here, I have pressure of a bunch of these different gases. And here is a dotted line here for our ideal gas. You can see that if I'm at low pressures over here on this end, that the lines are varying not as far away from the point of the ideal gas. And as I increase the pressures, you can see that my lines are moving further and further away from this experimental data. If I look at the graph on, let's see, the right, okay, this doesn't look like you can see this. Some of this got cut off. This is 293 Kelvin, 673 Kelvin. So this is a diagram of an idea of one gas, whatever gas it is, and they have taken and increased temperatures. And you can see at high temperatures over here at 673 Kelvin that the gas is behaving much more ideally than the other two. So again, it goes to support the idea that gases behave more ideally at low pressures and high temperatures. And again, we are taking out, let me get that out of there, sorry. We are taking out all kinds, okay, sorry about that, had to move that out of the way. I forgot what I was saying, but we are taking, we are not taking into account all the forces that are really happening with the real gas. And we talked about be the gas molecule in the classroom and its straight line motion and all these different things. There are forces, but if we take into account every single thing that's happening within a gas, our head would be spinning. We wouldn't be able to study them. So we are going to streamline it and study them at low pressures and high temperatures. So here are some volumes for the gases at 0 degrees Celsius and 1 atmosphere, which is 1 mole of any gas, should be 22.4 liters that it's going to take up of space. Now, if you take a look at these different values, you can see that they're all at the same temperature, they're all at the same pressure, and they are varying from our 22.4 liters, which is at STP. And you can see down here that ammonia is varying the most. Well, why is that happening? Well, of the ones that I have listed, you're going to see that there is some attractions going on there. And so if I were to draw ammonia for you, ammonia has a lone pair of electrons. So if I look at ammonia, it has these lone pair of electrons. So this side is slightly positive and this side is slightly negative. It has a greater differences in the charge, and so it's going to attract, have more attractions between the molecules. So my next molecule coming in is going to have attraction here to these lone pair of electrons of my nitrogen, and those forces are going to cause more deviation here away from Avogadro's law of 22.4 liters. So if there is a polar molecule, which is what this would be, uneven charges there, there's going to be more deviation away from Avogadro's law or on Pivnert PV equals nRT. Okay, so next we have this equation here, or question here. I will be talking about these in class and working through them with you if you have some trouble. And let's see, it asks for what volume of oxygen gas. So if you get an answer of 1.51 liters of oxygen gas, you have done that one correctly. You are going to have to write an equation and do some little bit of stoichiometry and putting it into Pivnert. So see if you can do that. And the next one we have here is also asking for a volume, how many liters of hydrogen gas are required to react with this iron 3 oxide. So again, there's a balanced equation there for you, and you just need to do some stoichiometry. So at the end, if you get 38.4 liters, you have done that problem correctly. And like I said, we will be going through those in class if you are stuck. Okay, so today we're going to talk a little bit more about the kinetic molecular theory of gases. I did a few demonstrations on that, and we talked about that straight line motion. So the first point here says volumes of particles can be assumed zero due to small particles and the distance between. I don't think I mentioned this, but I talked about that that gas molecules are moving really fast. If we were to take an oxygen molecule and calculate how fast it can move, it could go from St. Paul to Detroit in an hour. That's how fast an oxygen molecule can move. Obviously, it's not doing that with all the collisions and everything that's going on, but they are moving very quickly. Particles that are in constant motion, the collisions of gas particles with the walls of the container causes pressure and also colliding with themselves. That constant motion is a really important thing. They are moving very, very quickly, as I just mentioned with my scenario of the oxygen molecule. Step 3 says gas particles exert no forces on each other, and they do not attract or repel. Now, this is a theory of ideal gases because I just showed you that the ammonium particle, they do have some attractions there. Again, if we were to study all of that, you'll see here in the third podcast all the alterations that we would have to do to our equation. It's not going to be as simple as PV equals nRT. And then average kinetic energy is assumed to be proportional to Kelvin temperature of the gas. So kinetic energy is proportional to the temperature in Kelvin. Now, it doesn't mean that it's a direct relationship, meaning that if one doubles, the other doubles. It's just going to be proportional. Okay. And one other thing that, a couple other notes that I have here is that gases can be compressed. We know that gases we can force it. Like if you think about your tire on your car, on your vehicle, you are compressing a lot of gas. You're putting a ton of gas into there, pumping it in when you pump up your tire. So gases can be compressed. And collisions are elastic, meaning the energy is conserved, which is a great thing because think about that tire. We want to keep it inflated. We have a closed system. We push all that gas in there. If there was some sort of reaction or energy wasn't conserved, our tire would never stay pumped up. So it is a good property that the collisions, the gas molecule collisions, do remain elastic. Okay, and then let's see. I think we will stop there because I think the bell is going to ring here in just a second. So I'm going to stop here. This is podcast number 2, and we will start the next one, number 3. Have a wonderful night, and I will see you soon in class.